So here we have a paired data. So a company claims that their fertilizers are engineered so that the plants will be able to take the nutrients easier, and therefore it's going to give better crop yield. And 10 farmers are trying to see if that's true. So you have this paired data. So what you have is a paired data. And we already know how to do this, right? What do? We just take the difference, right? And see what the average and the standard deviation is. What test do we use?
Two samples. Two samples.
Yeah, two sample. What test? What kind of test?
Chive test?
T.
T-test. We use a T-test. Two sample T-test. So you subtract, let's see, what's A minus B? That's -6, -2, -2, +3, +3, -8, -5, -3, -3 again, and then -7. So the way you were taught so far is that if you have such a situation, then you just take difference and then you calculate the average of this quantity. Also calculate the standard deviation. You can just do this in your calculator. Just type these in to your calculator, list one. Yeah, maybe let's do it. Can you try? Type in -6, -2. So once you do the one variable statistics, tell me what you get as the average.
-3.
X bar is -3. 3.1. Just negative.
It's just negative.
Just -3.
And what's SX?
3.771.
So if you were to do two sample t-test, you're going to do the following. Since my goal is to explain to you something else, I'll not write all the steps because that's going to be too much. It's just that the null hypothesis is that mu has to be 0. The average difference is 0, that there are no difference between this brand name fertilizer and a generic fertilizer. An alternative would be that brand name is actually bigger, so this will be negative. So that's what you get, right? So your test statistic will be t equals to your -3 is this is from the sample. Your purported average under the null hypothesis is 0. You divide it by 3.771 over square root of 10. And can someone do this for me? What do you get? You get 3 point something. -2.1. -2.78.
-2.51.
Okay, -2.51. Okay. All right. So using a calculator, you can get that, and now you go look at the t-table. But t-table requires degrees of freedom. What's the degrees of freedom?
9.
9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points minus 1, so degrees of freedom would be 10 minus 1, which is 9. So you look at the, well, we first should have done T alpha over 2, which is not alpha over 2, T just T alpha, but it's a one-side, one-tailed test. And let's say our confidence, the significance is 0.05, so if you do inverse T of 0.05 with degrees of freedom 9, what do you get? You get negative
1.83. Yeah, 1.83.
Oh, that's okay. All right, so that's the critical value. This is less, so it's this negative 2.51 belongs to the left side. So definitely, we have proved that the null hypothesis should be false. And we accept, so we reject the null and accept the alternative, which is to say that
There is a difference.
there is a difference. Yes, the brand name fertilizer does do something. Okay. Now, there is something that I failed to stress, and even I would sometimes not write it, I would forget. And this is a very important assumption when you apply the t distribution. It's that if you're using t distribution, you're assuming that your data is normally distributed. That's an assumption, okay? So so let me write this down because it's important. However, t-test can only be used if the data is normally distributed. Okay? That's needed. And in many cases, it's quite reasonable because when it comes to amount of corn produced in the land, of course, it's going to vary, but it's not going to be very high or very low. The amount of corn, if you divide large amount of land in acres and you count how many bushels were produced for each plot of land, you are going to get something like a bell curve. So this kind of makes sense. Yeah. But you have to know that t-test assumes that we have a normal data. And if you have normal data and another normal data, and then the difference is again normal, that's another property of normal distribution. If you add or subtract two normal bell curve shapes, then the resulting data will also be normal. But let me try to elaborate a little bit more what t distribution is. So, what is t distribution? Now, I wish I could have explained this earlier in the semester, but the trouble with this is that usually chi-square distribution is taught much later. And to understand what t distribution is, you need to know what chi-square distribution is. So since we learned chi-square distribution, I can explain what a t distribution is now. Okay. So suppose we have some x that follows a normal distribution with average mu and variance sigma squared. If that's true, then if you take x bar, which is like a sample mean of n items, then what happens to the variance? Does it go up or down? The variance goes down, right? How?
Divided by square root of n.
Oh no, it's sigma over square root of n. That's the standard deviation. Over here, it's variance, which is squared, so this is n. Okay. Or you might just rewrite like that. Okay? So that's what happens. And therefore, if you take any sample and take the mean value and subtract from mu and divide it by sigma squared over n, actually this one, sigma over square root of n, and call this as z, and what's going to happen is that this is going to be following the standard normal distribution, because what is this doing? Subtracting mu shifts the entire data so that the middle point is 0, and then dividing by the standard deviation shrinks it down so that now the wideness of the data is 1. Okay? Standard deviation gives you the width of the data, right? So that's what happens. But the problem with this kind of approach is that in most cases you don't know what sigma is. Right? Yeah. When you do hypothesis testing, you're going to get a sample, and the null hypothesis is a hypothesis about the mu, right? So you can calculate this, you can calculate this, but you don't know what sigma is. So instead of sigma, what do we use?
SF.
Sx, which is the Bessel-corrected variance standard deviation from the sample, right? So instead of that, what we do is we take x bar minus mu and divide it by Sx over square root of n. That's what we do, and that's called the t-distribution. But if you look at what this is doing, see, this is same thing as sigma over square root of n times Sx divided by sigma, okay? Divided by sigma. And then this much is your z, right? That's your z. Do you agree? It's the same thing as that, right? Why are these the same? That's because sigma and sigma cancels. If you just simplify the right side, the same as this, right? So you just have Sx and the square root of n there. So these are the same. But then this much is z, and you still have this. And if you think about what Sx is, Sx by definition is this square root of 1 over n minus 1 summation of x minus x bar squared. Right? And that just screams chi-squared. Because what is chi-squared? It's the square of the normal distribution. So if you have some kind of random variable that fluctuates like a normal distribution, then its squares follow the chi-square distribution. And then chi-square distribution have something called degrees of freedom, which tells us that the shape differs from depending on how many squares you added. But if you look at this, although you're adding n squares, its actual degrees of freedom is n minus 1, because, see, this x bar really has xi's in there. So if I call this xi, x bar is really x1 plus x2 plus all the way up to xn. You divide by n. That's the average obtained from this sample. So the sum of the variance it tries to fluctuate is kind of dampened because you're subtracting the same value. So there's some complicated mathematical arguments here, but at the end of the day, this is going to fluctuate, or the value of this thing is going to be randomly distributed, like n minus 1 degrees of freedom chi-square distribution. Does that make sense? Kind of. I'm not giving you all the math, but that's what's happening. So, and then if you divide by sigma, this goes inside, so you get this sigma and then squared, and that one really is normalized so that this thing does behave like a square of the standard normal distribution, n minus of them added. So what ends up happening is this Sx over sigma behaves like a chi-square distribution with n minus 1 degrees of freedom. Okay? And that's what T distribution is. T distribution is really a normal distribution divided by some chi-squared distribution, and it has n minus 1 degrees of freedom. Okay? Now that you finally saw what T distribution is, so I kept saying, what is a T distribution? It kind of compensates for the fact that we don't really have the sigma. We're using our Sx to be approximate of sigma, and that kind of makes it more uncertain. So the curve, T curve, is wider than the normal. And that's like, this is the actual mathematical formula that was used to figure out the T curve. Okay. Yeah, but coming back, you kind of see, once you write down the formula, you kind of see the following, that T distribution requires you to start with the normal distribution. I started with the assumption that X follows the normal distribution mu sigma, right? That was my initial assumption. This is very much needed if you want to use this. If you don't start with the normal distribution, you can't use this because you're assuming something here. You're assuming you can use Z. Using Z means it's normal. And as I said, in many cases that's okay, but sometimes it's not. I mean, when I gave you some assignment to try the central limit theorem for real world data, and when you went out and picked your own real world data, how many of you saw like very good bell curve to begin with? Maybe 2, right? 3. But most of you saw something that's very skewed, right? Either skewed right, skewed left. That's what you saw, right? And if you have a data that's highly skewed, then this will be very dangerous. Now, if the sample size n, the small n here, if the sample size n becomes quite big, that's not a concern. Why?
Because it corrects
What corrects?
standard deviation.
Not the standard deviation. What corrects the not being normal? That's what's called the, come on.
Missile correction factor?
Huh?
The missile correction factor?
No.
Experience?
Hmm?
What's the chi-squared?
No, central limit theorem. What is the central limit theorem? It says if you take, you can begin with any kind of initial distribution. If you take the average of sample size, say 50 or 100 or 1,000, as you increase the sample size, the X bar is going to look more and more normal. So what that means is that when you have a big enough sample size, you don't really need perfect bell curve to begin with. If your original X is not exactly normal but somewhat normal, that's good enough. Because after some increase of sample size, it will be normal, and then you can use the Z. Okay? I said, like, oh, if it's 30 or more, you can just use normal distribution, which, by the way, it's not a standard thing. Many professors nowadays say whenever you have Sx instead of sigma, always use T, which is more correct one. I kind of what I'm teaching as 30 as like the dividing line, that's more old school. Nowadays, people just say this should always be t distribution, not a z, even if number of data points is bigger than 30. But anyways, if it's bigger than 30, the central limit theorem kind of takes over, and you're justified in using a normal distribution. Okay. But then when your sample size is small, then it's kind of dangerous. If it's very skewed to begin with, this, even after taking account of the fact that you're using Sx not sigma, is not going to be good enough to fix your analysis, statistical analysis. So because of this important thing, you have to do what's called a non-parametric test. So you don't have to assume that the data, this data or this data is normal. Yet you can calculate some probability and say, hey, this is highly improbable if their averages were the same. And we can deduce some calculations. So let me show you first a very simple approach called the signed test. And then once this is done, I'll show you another, a bit more involved calculation, which is called the Wilcoxon signed rank test. Okay. And then there are some other, okay, let me also write that. Such a test is called a non-parametric test. Okay. The t-test is assumed to be a parametric test because, well, for example, a normal distribution has how many parameters? How many parameters does a normal distribution have? 2. What are those 2? Mean value and standard deviation, right? You only need two parameters to describe normal. In fact, if you know these 2, it completely determines the normal distribution. Whereas if you say, oh, there's some distribution, I don't know what kind of distribution it follows, then whatever can be, we don't know, right? So those are, if a distribution is completely unknown, then it doesn't have any parameters. It's a non-parametric thing. This is a parametric thing. It has 2 parameters, okay? So when we say non-parametric test, it means that our statistical analysis does not depend on normality. And that's sometimes important. So in some fields like biology, when you do lab experiments and you have to show something using statistics, sometimes they would be required to do the non-parametric one over the parametric one because for certain measurements it's more likely to be highly skewed and you can't use normality for those cases. Okay? So let me first give you something called the sign test. And I'm just giving you a very simple version of sign test because this can get a little bit more complicated, but this is not as widely used, so I'll just give you a very easy version of sign test, and then we are going to move on to Wilcoxon signed rank test. Okay? So what is the sign test? First of all, you have to know that in these non-parametric tests, we use medians instead of means. Okay? So let's think about the following. If the generic and the brand had the same median, note that I'm saying median, not mean. Okay? So our null hypothesis is that generic and brand has same median. Okay. Then, if you look at whether it's a minus or plus, what would you expect? You would have about the same number of positive and negatives, don't you think? Right? Yeah. Because if they have the same median, or if they're from the same sample that has the same median, right? So, or let's just say here's one probably the distribution, another one, it could be wider, it doesn't matter. But the important thing is that their medians are the same. Then if you randomly pick a point from the second distribution and then you randomly pick a point from the first distribution, the probability that the first can be more than the second, or vice versa, will both be what?
0.
No, probability can, 0 means it never happens, so it does happen. So probably that sample 1 value is bigger than sample 2 is what? If they have the same median, what? Okay, so all right, let me just ask like this: if you have a median, what's the probability that any random sample is above the median?
50%. 50.
50%, because what is median? Median is like the point where it's exactly the half, right? If you find the median, 50% of the data is above the median, 50% of the data is below the median. Is that right? Yeah. So you have 50% chance that it's above the median, 50% chance that it's below the median. Okay? Now if you have two samples, what's the probability that one will be bigger than the other? Again, 50%. Because it should be the same as, it shouldn't matter because above, I mean, see if you have two probability distributions that have the same median, if you subtract them, you end up with a symmetric probability distribution centered at 0. So their difference will be picked from here. So you would have 50% chance that you get something positive, 50% chance that something negative. Okay? That's what you have. Now, if you're dealing with data that gives you only integers or somehow somewhat rounded to nearest integers like this one, it could be that the difference is 0, but those we just don't count. Okay? So here's what the sign rank test does. I know that there's 50% chance of having a minus and 50% chance of having a plus. So now it's like looking at this as if it was a coin flip. If you flip the coin 10 times, you got 8 negatives and 2 positives. Is that a fair coin?
No.
What's the probability you can have something like that?
Very, very,
Really
very,
low.
Very low. How would you calculate that? What kind of probability distribution is that? It's called the... Do you remember the probability distribution for a coin flip? You learned early in the semester.
Binomial.
What?
Binomial.
Binomial. Very good. It's binomial. Binomial probability with 10 trials, and probability is 0.5, right? So that's what number of, let's say number of positive coin flips. Okay, so X is number of positive coin flips, which is positive. So what we are trying to show too is, if this is true, what's the probability that X will be 2 or less? Highly unlikely, right? Because you would expect about 5, right? If you get 4 positives or 6 positives, yeah, that could happen, right? But if you only get 2 positives, that's really suspicious, right? So you do this, which is binom CDF. So please use your calculator to help me out here. With 10 trials and X is equal to 2, where probability is 0.5. I think 0.5 probability, and you're looking for 2 or below. What do you get?
0.055.
0.055. So so if our significance level is 0.05, we're not quite there, but it's very compelling, right? Yeah. You would say that there's only like 5.5% chance you would get only 2 or less positives when you do such a thing. Okay? So you can say that if it was like significance level, say 8% or 10%, then we would say with significance level 10%, we can reject the null hypothesis and say that really the brand fertilizer is doing the better job. Okay, so that's called sign test. Kind of makes sense, right? Now, in general, if this in general, sign test would usually have a lot bigger data here, bigger sample here, and then because it's a bigger sample, you can use this BNP approximated by normal distribution with NP and NPQ. Average NP and NPQ is the variance. I talked about this briefly a long time ago. But you can use this, so there are some other formulas associated with this, but that's not my goal, so I'll just leave it at that. And I'll now explain the more important thing, which is the Wilcoxon signed rank test. Now, we just did the sign test, and although the sign test itself kind of makes sense, there is something that leaves us wanting, and the fact that is that even if these were positive, it's not very positive, right? If you see the entire data, there are some negatives that they're very negative, like -8, -7, -6, right? Whereas this 3 is positive but not very positive. So you might think, well, in the sign test, you're not really looking at how large something is and how negative something is. Maybe if you include them, you might have a better test. And that's exactly what the Wilcoxon signed rank test is doing. And what it does is, first, so you have to calculate ranks. Okay? So number 1, calculate rank. And that requires a few steps. So first what you do is take absolute value of differences, okay, and order from smallest to largest, small to large. Okay, so let's do that. So what is the smallest absolute value one? Here.
2.
2, right? So -2 becomes +2. So you have 2 and 2. Okay. And the next values are?
3.
3. How many times does it appear?
4.
4 times. So you have 3, 3, 3, 3. Okay. And
5.
Then the next one is, do we have 4? No 4. 5 appears once. 6 appears once. 7 appears once. 8 appears once. Okay. So that's what you do. And then number 2, rank them. I need a different color. So I'm going to rank them beginning to the end. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I've ranked them. Okay. And then handle ties if you have a tie, see, I've said this is 1 and that's 2, but they have the same value, so it's unfair to say this is 1 and that's 2, right? So we need to handle ties, and the way you do it is by taking averages, okay? So average of rank. So we take the average of the rank number whenever there's a tie. So here we assign rank 1 and assign rank 2. What's the average of 1 and 2?
1.5.
So instead of 1 and 2, now the new rank will be 1.5 and 1.5. Okay? And then 3, 4, 5, 6 have the same number. So now we have a tie here. So what should you do?
Add them up and take the average.
Yeah, 3 plus 4 plus 5 plus 6, and you divide it by
4.
4. Okay, that's 9, so 18 over 4,
4.5.
which is 9 over 2, which is 4.5. So you have 4.5, 4.5, 4.5, 4.5. Okay? And then the other ones are okay. It's 7, 8, 9, 10. Okay. And once you have them, then you go back and write these rank numbers. So what you have is -6 was, rank number was 8, so this is 8. -2 was rank number 1.5, -2 is 1.5. 3 had rank number what?
4.5.
4.5. 4.5, 4.5. 8 had rank number
10.
10. 5 had rank number 7. 3 had rank number
4.5.
4.5. 4.5. And then
9.
9. Okay. So you have that. And then after calculating the rank numbers, you're going to define two things, T plus and T minus. And these are some of the ranks for positive numbers and some of the ranks for negative values. So those are named T plus and T minus. Okay, so let's look at the T pluses. Which are some of the ranks of the positive ones?
4.5.
4.5, 4.5. Okay. So it's going to be 4.5 plus 4.5. That's going to be 9. Right? Okay, what's the sum of the rank of the negatives? Well, that's a lot. It's
45.
8 plus 3, so it's 11. Plus 17, that's 28. Plus 9, which is 37. And 46. Am I right? Okay. So you get 46. Okay, that's your T minus. Let me do it again. 8 plus 3 is 11. 17 plus 11 is 28. Plus 9 is 37. 37 plus 9 is 46. Good. So that's 46. Okay, you get the sum of ranks of the positive ones, sum of the ranks of the negative ones. Okay? And that's going to be our test statistic for the Wilcoxon signed rank test. Okay? So now let me explain what the Wilcoxon signed rank test does. So it's still the same four-step hypothesis testing. So H0 is the medians are the same. Okay? And the alternative is that they're not. But you can use a two-sided test or one-sided test. So if you're using the one-sided test to prove that brand name is bigger than generic, you're going to say that the median of brand is bigger than generic. That's your alternative. Brand median, generic median, that's your alternative. Which in our case, because we computed the difference by subtracting, no, let's not go there. Okay, so that's our alternative. Okay, number 2, now we have to figure out the rejection region. And I just realized that I made copies of this table for the Wilcoxon. I didn't bring it. I'll bring it right after this. Okay, so if you see it, for sample size of 10, and if it's one-sided with, in the table you'll see that one-sided with alpha equal to 0.05, the critical value will be that the t has to be equal to 9 or less. The critical region is t 9 or less. That's your t critical. Okay, number 3, you have to calculate the test statistic. And test statistic is calculated exactly following the previous thing that I explained, which is you compute t plus and t minus using the previous I recorded. And the minimum of that is defined as our t, which is the test statistic. Okay? But what's the minimum?
9.
9, right? So it barely worked. Okay, so this is 9, and because 9 is 9 or less, our conclusion is what? We reject the null. Okay? We reject the null, or H0, and accept that median of brand is higher. So, in other words, brand, if you use a brand fertilizer, it will give you higher yield. That's what we proved. Now, let's compare. So that's it. That's a Wilcoxon signed rank test. Now, let's compare between the 3 things that we did. So first, we tried the t-test. Yes?
So for step 3, you just take whichever one is lower and compare that to...
Yeah, minimum means you just take whichever is lower. There is, however, one thing. Thank you for asking that question, because I forgot to say one thing. Now, because this one it's not negative for one-sided tests or plus. This one doesn't have a plus or minus. These are always positive, okay? So when you use the Wilcoxon sign test for a one-sided test, you have to be very careful. And the thing that you have to be careful is that if you're doing one-sided, make sure that your data is pointing towards to that direction. See, if you mistakenly want to prove that brand is actually less than generic, you calculate everything, it will still give you 9, and you might mistakenly conclude that, yes, the brand name is less than generic, but that will be wrong because you see that on average, the generic did worse than the brand, right? So you can't use this data to prove the opposite inequality because it doesn't make sense, okay? So this is one thing that you have to be careful about when using Wilcoxon sign test. Because your test statistic is always positive, it doesn't distinguish it between the left tail and the right tail. So you have to use the data itself to figure out whether you are applying this correctly, okay? Does that make sense? All right. Okay, so now seeing this, let's now compare all 3 methods that we've done. So first we tried the t-test, right? And the p-value came out to be something like 0.02, very low. And if you're using t-test without question, of course brand name is much, much better, right? Yeah. It's sort of a result that the company would very much like, right? On the other hand, when we use the sign test, we got somewhat of a significant thing, but the value, p-value was 0.05, so it was above our significance level. So if we really stuck to 0.05, that would have been insignificant, okay? And when we use the Wilcoxon sign rank test, it's slightly better because we are including the seriousness of how one is outperforming the other. When that was considered also, then we still had a significant result, although it barely did. Okay, and that means what this tells us is that Wilcoxon sign test, although it's stronger than the sign test, the regular just sign test, in getting this rejecting the null hypothesis, it's weaker than the t-test. But why? Because t-test assumes something more. T-test assumes that you know that the data is normal, whereas Wilcoxon is operating with less information. So you can't really distinguish as well as the t-distribution. That's the difference, okay? So this is something that you should also know. Whenever you do a parametric, non-parametric test, then you always have the non-parametric test being weaker than the parametric test. But even if that's the case, in many cases, especially when you're trying to publish something in a journal, you might be forced to use the non-parametric test because you can't guarantee the normality of your original random variable, all right? Okay. So I just realized something. This is 10, right? Do you see it? What's our n? N is 10. So this is 10. So this is less than 10. So the conclusion is the same, but my comment about 9 was wrong. Okay.